If f is a scalar function of two variables, so f of xy equals z, then the gradient vector del f of xy has as its components the partial with respect to x times I plus the partial with respect to y times j. And note that this takes a point xy in R2 and it maps to it a vector. It maps it to a vector in V2. That's the notation we use to say that it's a vector. The outputs are vectors. But the point is, if I'm taking a point in from R2 and I'm mapping to a vector in V2, then the gradient vector that we've seen before actually turns out to be a vector field. It's called the gradient vector field. We can say the same thing if our original function was a function of three variables. We'd still have a gradient that would map R3 to V3. The relationship between f and del f gives rise to a classification of vector fields. If a vector field f is the gradient of a scalar function, that is to say, if the vector field f is del f, the gradient for some function lowercase f, then the vector uppercase f is called a conservative vector field, and lowercase f is called a potential function for uppercase f vector. Just to remind ourselves of what the gradient vector looks like, we're going to find one. We're going to find the gradient vector field of f for a function f of xyz equals x squared y times e to the y over z. First, we get our partial derivatives. We need the partial with respect to x, the partial with respect to y, the partial with respect to z. I recommend you go ahead and pause the video so that you can crank them out. For the partial of f with respect to x, y e to the y over z are constants. We differentiate the x, so we have x squared, so we have 2xy e to the y over z. For the partial with respect to y, we are considering that we have a product in terms of functions of y. And so we have u prime is x squared e to the y over z, that's u prime v, plus uv prime. V prime with respect to y is going to put a denominator of z into our term. And so we have x squared y over z times e to the y over z. And then finally, the partial with respect to z is equal to negative x squared y squared over z squared e to the y over z. The negative and the denominator of z squared are coming about because of the chain rule, because with respect to z, our function really is e to the y over z, with x squared y acting as constants. I'm actually going to write the partial with respect to y in a more compact form. E to the y over z times x squared times the quantity of 1 plus y over z, just a little bit easier to write. And now we can put this all together. So del f of xyz is equal to 2xy e to the y over zi plus e to the y over z x squared times the quantity of 1 plus y over z j plus, nope, that's a minus, x squared y squared over z squared times e to the y over z k. Let's look at one more. Find and sketch the gradient vector field del f of the function f, which is f of xy equals 1/2 x squared minus y squared. Again, I recommend that you pause the video so that you can do the work. Don't start it up again until you have the vector field and some representative vectors in the vector field sketched. Our partials turn out simply to be x and negative y. And I've drawn a few representative vectors, well, more than a few. So the question might be, how many do I need to draw? I would recommend drawing some in each quadrant. And then it's just enough so that you can see what the field kind of looks like, and so that you can communicate that to whomever your reader is.